Now, we alluded to what we were going to be talking about today the last time we met. And for some of you are going to think, boy, we're kind of going slow about this stuff, aren't we? Well, yes, we are, because as we get deeper into it on later today and tomorrow, it really starts getting thick. So I want to give you time to absorb everything that we're talking about. But last time we met, we took this curve that we've got right here, y equals x squared, and we rotated it about the x-axis. And we said when we do that, we found out that we come up with something that looks kind of like a horn, and we were able to find the volume for it. And if you remember, when we were rotating about the x-axis, what was our base formula that we were integrating? Do you remember? Pi r squared. Okay, and we were integrating from one end to the other, and we were integrating with respect to x because we were going about the x-axis. Okay, that was our basic formula. And we talked about, we got this really from pi r squared h. Remember, pi r squared is kind of the area of the circle, h is the height, and the integration somehow magically takes care of the heights for us in there, okay? So that's what we talked about last time. Today we're going to take the same problem to begin with, but now we're going to rotate it about the y-axis. Okay? So just to give you an idea, here's what the figure is. Now if we're rotating it about the y-axis, our discs are going to be coming out of the wall, and they're going to be going around this way. So we'll have a little small disc like that all the way around. And if we actually do integrate it, we get something that looks, how do I turn this thing? There it is. There we go. Something that looks like that. So that instead of a horn shaped that gets bigger, it looks more like an awkward looking bowl, a thimble, something like that. So how do we find that volume? Well, now let's talk about it for a second. If you look at it from the end right here, you see it's kind of circular once again on the end. So that would lead you to believe that pi r squared would work again. But what's different this time around?
We're going by the y instead of the x.
That's right. We're going around the y-axis this time. So how do you think, what do you think that changes if you're going around the y-axis? The r, okay. So what does our r need to be? What does our radius need to be? Our radius now needs to be the distance this curve is from the y-axis. Before we were talking about the distance it was from the x-axis. So it was y equals x squared. Now we want to know the distance it is from the y-axis. Yes, sir?
So the x equals the square root of y.
That's right. So we're going to need to take this equation and solve it to get x equals the square root of y. So our distance now, our radius, is going to be the square root of y squared. All right? What else changes? Now, because we've written that down for our radius, we've still got the pi out here. That's right. We are doing dy because our function in here is with respect to y, so it's dy, and our limits of integration also have to be y. They are from this point down here, 0, up to this point right here, 0 to 1. Okay? The key thing for you to remember in this is dy means that the equation that or the expression we're integrating has to be y. It means our limits of integration have to be y. Now, I can virtually guarantee, well, I can't guarantee anything. I can tell you for the last 7 years, there has been a problem on the little test you're going to take on May the 5th, asking you to take some shape and rotate it around an axis. It's a 3-part FRQ. You always find the area of it, You then rotate it around an axis, and then you find the volume with known cross sections. For the last 7 years, that problem has been on there. So I can safely say, I think, that it's a high probability that it will be on there once again this year. It's been an area of focus. That's Monday, okay? That's when we really get out there and deep. So integrating this is not that complicated because the square root of y squared is y. So we're just integrating from 0 to 1 of y dy, which is, oh jeez, why won't it work? Y squared over 2 evaluated at 1 and 0, which is going to be 1/2 pi, or pi over 2 is what we would get. So that would be the volume of this shape that we've got right here. And if you look up here, this is what the volume, they found it to be 1.57. So somebody built that out correctly. Divided by 2. Yeah, that's right. So pi divided by 2. Okay, so then our formula for around the y-axis looks very similar. It's dy, it's limits of integration here, and it is a radius or a distance from the axis that we're rotating it around squared. Again, pi r squared. Everything is y's this time. That's the only thing that's different. Everything is y's. Now, on the little test that you're going to be taking in May, on the mock exam that you're going to have next Friday, you need to understand these can get complicated as we go deeper into it. You need to get every point you can by putting down on the FRQ. If you put down the correct things right there, dy and pi, you're going to get a point out of this, okay? If you put down A and B correctly, you're probably going to get a point out of it. And if you get the correct answer, you're going to get the third point. So even if you aren't certain, write down something so you can hopefully get some points out of it there every single time. All right, let's look at the next problem, and let's see if you can handle this one by your lonesome here. Set up and evaluate the integral that gives the volume of the solid formed by revolving the region around the y-axis. Almost. It's very similar. I agree with you. Very, very similar. Yeah. It's a little bit bigger. Yeah. It's identical but not identical. So yes, the integration part shouldn't be hard to you. Just noticing, I want to be sure that you get the right limits of integration because that's a common mistake. These are almost always part of the FRQs that you can do with a calculating device. So if I were you, I would write that down on my paper, put an equal sign, and write down whatever my calculator gave me for the answer. These expressions in here oftentimes are going to be very challenging to try to integrate by hand. But since I don't have my calculator out right now, 0 to 4 is 16 over 2. It's 8 pi. Okay? Anybody got a problem with that? All right. Let's look at this expression. Now, how do I know that I'm rotating about the y-axis here? Because that's the problem? Yes, the rectangle is an indication that we're rotating about the y-axis here. Also, this little symbol right here tells me we're rotating it around the y-axis, okay? So whenever you see this symbol, you should know immediately, I'm dy, pi, write that down. You ought to be able to even get your limits of integration, so you've got a point or two no matter what out of that. And you could probably, some of you, I can see the wheels turning, you can say, okay, I know what that figure would be like, so I can find the area without calculus. And that's a great place to be, but find it with calculus anyway. be sure that you know how to solve this thing for x. So it's 16 minus y squared equals x squared. Now, when I actually solve it, I get plus and minus 16 minus x squared. Which one is it? Is it the positive one or the square minus y squared? How do we know it's the positive one? You're correct. Well, we're going to square it anyway. I mean, when we stick something in here, we're going to square it anyway, right? So it really doesn't matter. But is this shape, is this in the first quadrant, x equals the positive square root of 16 minus y squared or the negative square root of 16 minus y squared? Do you know how to tell that, I guess, is what I'm asking. It's the positive one because where is the curve? It's up and to the right. It's in the first quadrant. It's above the x-axis, so that means the y is a positive. It's to the right of the y-axis. That means the x is a positive. So we're simply integrating 16 minus y squared, and that's going to...
Square root of 16 minus y squared?
Yes, the square root of 6, because you have to solve it for x, not for x squared. And then when we square it, we're going to be integrating 16 minus y, so that'll be 16y minus y cubed over 3, evaluated at 0 and 4. In this case, if I had missed this completely and just integrated square root of 16 minus x squared from 0 to 4, I'd get the same answer. Because this is a half of a sphere is what we're going to be making. Can you visualize that when we rotate this thing around, we're going to get a half of a sphere? We're going to get the top half of a basketball? I'm assuming y'all could finish that off there. I'm certain that y'all... What did y'all get for a final answer there? What pi? You're going to get 64 minus 64 thirds. What is that? That's 2 times, that's 128 thirds pi. Something like that's what I got. All right? 128 thirds pi would be the volume of that. And it would look like a ball. Well, shapes like that are not very interesting to continue doing all the time. What happens with this? Set up the integration. Don't actually integrate this one yet. Just set it up so that we can talk about it a little bit. How do I solve, Wesley?
Since the x would be, if you put in the there terms of the cube root of x squared, y will become y cubed squared. Or not y cubed squared, the square root of y cubed.
Right. In order to solve this, you've had to do this from time to time. You need to raise both sides to the 3/2 power, because that will get the 2/3 power to cancel out. So we get x equals y to the 3/2 power. So we're integrating y to the 3/2 power, and our limits of integration are 0 to 1. Where am I getting that 0 and 1 from? The y-axis, okay? Yes, I'm going to drive that home because when we start mixing this up, it's going to be easy to get that confused. So when I integrate that, that becomes 2/5 of y to the 5/2 evaluated at 0 and 1. Ooh, square it. Thank you. Thank you. Ooh, yep, I forgot to square it. So we square it, and then when we square it, we wind up with just y cubed. Right, so then it's y to the 4th over 4, evaluated at 0 and 1. So we get 1/4 pi. Any confusion there? All right, good. Set up but do not evaluate. Set up but do not evaluate. This is a good time to talk about instructions on the little test in May. There will be some problems, or if the problem says set up but do not evaluate, follow the instructions. Write down the integral. Don't try to solve it, because if you solve it wrong, we're going to count off. If you just set it up like you're supposed to, that's all you have to do. So we're integrating dy. How is this one different? Wow, it's just blah. Y squared plus 4y, quantity squared, pi. What are our limits of integration? 1 to 4. 4 to 1 if you're going top to bottom, okay? All right. We're about through boring you, okay, because now I think we get to a challenge. Yeah, you could go ahead and solve it if you wanted to, but I'm confident you could do that. This next one is a challenge. What you think? So you rotate it around the x-axis? Okay. We're rotating it around the x-axis, Kevin points out, because we know it's going to be dx. We're rotating, so we know it's going to have a pi. Can you tell me what our limits of integration are? 1 and 0. Okay, boom. We've got our 1 or 2 points already there. What's different about this one? Find the area between the 2 curves. Yeah, we've got 2 curves in here. So can you picture what this is going to look like when we take this little blue region here and we rotate it out of the board and back through? What are we going to wind up with as far as a shape? It's not going to look like a funnel. It's going to look more like it's going to have actual volume. Actual volume in here. Yeah. So do you see? It's going to look. If I'm looking at it from the outside, it looks like a funnel. But if I look over inside of it, there's actually a wall inside the funnel. So there's air between those two. So it's not just the volume inside of the shape, it's the volume of the shape itself. Well, yes, there's going to be volume in this blue area, and what we're trying to find is what is that volume in that blue area. Kind of like this $35 cup here. Did y'all know that this $35 cup has 2 walls in it? Yes. That's the reason it can keep the stuff so cool. And they may put something special in between them. I don't know. The Yeti. Okay, so it's kind of like this. You're going to have 2 walls to this. All right, so I want you to think about for a second, how would you physically make this thing? I guess you take 2 pieces of something stick them together. Okay. Yeah. If I set a block of wood in front of you, there it is. How are you going to carve this thing? With a saw. Okay. But what you're going to have? What are you going to have to do? Measure it out. Okay. Okay. You're going. If I've got a block of wood here, let's. Ooh, I'm not very good at it. Let's have a circular block of wood. Okay. Here's my block of wood. Okay. So what have I got to do? I'm going to have to figure out a point down here at the bottom of it, and I'm going to have to start chipping away on the outside, aren't I? I've got to cut all of this stuff away, and then I've also got to dig out this stuff in here. So unlike the other things that we've had where we only had 1 wall in there, we've got 2 walls inside of this. So how are we going to do this? Let me tell you what in my mind I'm doing here, okay? I am going to, if I'm going to make this thing, I'm going to take this top curve, this top curve, and I'm going to rotate it around. Okay? That's going to make my outside figure, right? And then I'm going to somehow cut out, according to this bottom curve, cut that out of the inside and scoop that part out. Then I've got my figure. Okay? How am I going to make just the top curve? How would I find the volume of just the top curve? Square the top. So it's going to be the top squared minus, how would I do just the bottom? Bottom squared. Remember a few weeks ago I said top minus bottom was going to keep showing up? It's going to keep showing up, okay?
So, basically you just square them both.
Yeah. Now, which one's the top? Is squared or the fifth the top one?
Squared.
Squared. How could you figure that out if you don't really know? I'd pick a number between 0 and 1, a half. A half squared is a fourth, and a half to the fifth is a 32nd. Yeah, so it's going to be top squared minus bottom squared dx 0 to 1 pi. So we're integrating x to the fourth here in this first one, so that becomes x to the fifth over 5. We're integrating x to the 10th, which becomes x to the 11th over 11, evaluating at 0 and 1.
So you can't just do top minus bottom squared.
Because if you did top minus bottom squared, that's making it into one wall. Top minus bottom, you're just getting one figure there. This would give us 1/5 minus 1/11, which is 6/55 pi. That would be our final answer there. And this is where it starts getting a little trickier, when we've got something that would have two walls in it. Because we could take those two walls, we could take that same figure and rotate it about the y-axis now, couldn't we? Would we get the same shape? No, because now it's more like a bowl with two walls. Rotating it around the x, we get a funnel with two walls. Rotating it around the y, we get a bowl with two walls. So we're going to be doing more with that, but I wanted to at least brief you a little bit on, hey, this is what it's doing here as we're moving forward there. Any questions about that so far? Okay, so if you're going around the y-axis, it's dy. Your limits of integration are y. If you're going about the x-axis, it's dx. Your limits of integration are x. It's always pi r squared, okay? Why did I do that a second time? We've already done the problem, so there's nothing else. Okay, you have a little homework 42 that some of you haven't done. You've got homework 43 that none of you have done that you can be working on. And you have one FRQ due this week, okay? FRQ 54 we won't be able to do until after tomorrow's lecture completely. So once we get through with tomorrow's lecture, then you can begin working on it for next Wednesday. I remind you that next Friday, you get to spend all morning with me taking the mock exam, and then you get to eat lunch and come back to calculus all afternoon because it ends first and second period. So we just get to be together all day on April Fool's Day. And no, it's not an April Fool's joke. Yes, sir. Help is officially in physics today.